Hello, my name is Juan Carlos Beltran, and today I'm going to be talking to you guys about positrons. What a positron is the antimatter counterpart of an electron. So the characteristics are the same: mass, spin. The only difference is charge. In case of charge, a positron is positive, while an electron has a negative charge. So the significance of a positron was that it was our first direct evidence of antimatter. They were first observed in 1923 in the Soviet Union by Dmitry Skobeltsyn. Um, but they were later proposed by Paul Dirac, the man, the myth, the legend. Um, he was working on a problem at the time, and the solution he came up with was that an electron could have a positive and a negative energy. So that's pretty big. So experimentally, it wasn't confirmed. 1932, Carl Anderson. Um, he ended up winning the Nobel Peace Prize for this, and he credited Skobeltsyn for this later because Skobeltsyn was the one that basically set up the experiment that confirmed this. And they weren't named positrons by Carl Anderson. They were actually named positrons by someone in the one of the journal editors of the Physical Review at the time. So the way the experiment worked was, um, you have a cloud chamber, and there's cosmic rays coming in from the atmosphere. So what happened was that the particles would enter the chamber, and then they would go through lead. The lead would stop them enough for them to view their trajectory. Now, later, for the experiment, they added a magnet. What happened was that the trajectory is bent, and they noticed that the electrons had bent one way, while the positrons would bend another way. So this was a clear um, indication that you had something that was like an electron, but it had a different trajectory under a magnetic field, and it couldn't have been a proton because they tested out protons and they had a different trajectory to the one that the positron had here. So where do they come from? Basically, come from all over the place. They seem to come from everywhere and nowhere at the same time. I'm going to specify this later. For now, let's leave it as is. So basically, one of the ways that we could get it here on Earth is beta decay. So when you have an unstable isotope, one of the ways that it tends to want to stabilize itself is through this process called beta plus decay. Now, there's different types of decay. You also have the negative one. I mean the minus, beta minus. So what this one does is that inside a unstable the nucleus of an element, a, a proton will release a positron and then turn into a neutron in order to try to stabilize itself. And through there you get a positron emission. Another way is from cosmic rays and muon decay. So when you have, let's say, high particle, high high energy particles like alpha particles or protons that come from various things like sun, other stars, they seem to be all over space. They interact with molecules in the atmosphere, and since they have a lot of energy, it collides the high energy particles coming from space, and then they collide with the molecules, creating a shower of particles. A similar phenomenon we recreate here on Earth with particle accelerators. So one of the things that you could get from that are sometimes positrons, and a lot of times you actually get muons. And the thing about muons is also a lepton. The only difference is that it's a more I guess it's a fatter lepton, but so a muon would then decay into an electron, as shown in the picture below. So a negatively charged muon decays into an electron, an antimatter electron neutrino, and then a muon neutrino. And it does this in order to try to conserve its charge. But the positive muon, that one decays into a positron, an electron neutrino, and an anti-muon neutrino. So that's another way that we could get positrons. But they also seem to come from all over the place, like I said. From space, they seem to come from supernova, pulsars, microquasars, dark matter annihilation, dark holes and pair production. I'll go more into that in a little bit. But for the most part, in a lot of these, more research is needed, especially in that dark matter annihilation. So one of the cool things about a positron is its interaction with an electron. When they meet on contact, what happens is that these two particles seem to annihilate into gamma rays. There's a limit to how many gamma rays you can get. You can't get one gamma ray because it needs to conserve energy. So the most common type of amount of gamma rays that we get from this is two, and that happens when you have when one of the particles has a spin up and one of them has a spin down. The annihilation creates two gamma rays. In cases where they have the same spin, up, up, or down, down, they end up creating three gamma rays. And the way you could think about this is uh, up, up. If you could think about it as waves, their superposition would be higher than the superposition of an up and down spin, thus creating more gamma rays. So here's a Feynman diagram of the electron, and then you have the positron, and right there you have them created two gamma rays. So one of the really cool things where they positrons seem to come from is these things called virtual particles. So they seem to be particles that pop in and out of reality. Um, Basically, they're caused more due to the quantum fluctuations of space-time. So I'll go into an example soon where I'll bring back in the black hole. But basically, this is limited by the uncertainty principle. As you can see by the bottom equation, it's basically telling us that the more energy, let's say, a virtual particle pops into reality with, the less time it's around. And vice versa, the more time that it's around, the less energy that it has. So virtual particles seem to come in pairs, usually in photon pairs, but sometimes they'll actually come in a positron and an electron pair. Um, one of the really good examples that we have is the best measurement in physics. I think they have it down to 14 decimals. And the thing is, let's say that a virtual particle pair of an electron and a positron pops in the middle of this hydrogen atom. So in between the electron and the proton. And what happens is that because it's in there, it actually makes the electron skip into one of its other quantum states. So actually, the light that it gives off, we can measure the frequency, and when the virtual particle comes into play, the frequency actually increases. So this could be measured, and I believe it was measured by Feynman. It was something he got the Nobel Peace Prize in, I believe. So one of the other things where this comes into play with the black hole is that let's say you have a positron and electron pair popping in near a black hole. If let's say that the electron goes inside the black hole, the positron is then left to wander around in space. Um, Eventually, it'll meet an electron and annihilate into gamma rays. But although it seems that we're basically getting nothing from nothing, I mean something from nothing, there's actually some validity to this. So what we have experimentally to prove the existence of virtual particles is something called the Casimir effect. So what the Casimir effect is you have a system where you vacuum out everything and you leave two non-conductive plates, and the plates you put them nanometers apart, very very short distance, to the point where certain wavelengths of light can pass through it. Um, the theory is, and of course we actually have experimental backup for this, is that outside of the plates you have different virtual particles, photons, and they crash into the outside of the plates. Meanwhile, inside, photons are very limited because of the space. You could only fit a certain amount of wavelengths in there. So basically, the momentum of the particles outside bump into the plates and they slowly collide into each other. Uh, so through this, we could tell that virtual particles are actually a thing. Uh, the other way was this system of the hydrogen atom, where a virtual particle pops into it. There's actually different applications for positrons. One of them is a PET scan where they fuse an isotope that has that goes through beta plus decay, and they inject it into someone, and then since the molecule that they injected into the person is then passed through the bloodstream, uh, it depends on the molecule too. Some depending on what they want to see. Um, inside the brain, for example, when they do a PET scan, the positron that goes under decay ends up interacting with an electron, and then you get the gamma rays. Uh, that gamma ray is then detected by a detector, and then using all that, they could make images of the brain. Uh, Another really good application that we could use is positronium. Positronium, what it is a system of an electron and a positron. It has a lot of similarities to a hydrogen atom. The only thing is that it's two leptons rather than the proton and the electron around it. The thing about positronium, though, it's pretty unstable. It annihilates quickly into gamma rays. Other two applications are high energy collisions or low energy collisions. So one of the ways I would use it would be for a gamma ray or an X-ray laser. So I would do this in terms of application. This would fall under um, low energy collision. So what I would do, I would find a way to store positrons in one chamber, electrons in another chamber. In the middle, I would have another chamber that has reflective material inside, as well as a geometry that lets gamma rays or any light basically pinpoint into one exact state or multiple states. I mean, multiple points that'll turn into one point. Uh, One of the ways that I would actually maximize my maximize the amount of gamma rays I could get would be through a Bose-Einstein condensate. So what a Bose-Einstein condensate would let me do is get every particle that I have in the system to have the same quantum state. That's to say, if I have some particles in an up spin and some in a down, and I put them in a Bose-Einstein condensate, I would basically get them all to have the same spin. In turn, when I do have the same spin for the electron and the positron, I could then let them annihilate into three gamma rays. And then from there, I would just focus it into a single point of light. Um, in terms of an X-ray, I would probably let the gamma rays pass through a certain type of material that will slow them down a little bit, or actually change their frequency or their wavelength. Um, but apart from this, there's basically you can use them for different applications. It's all limited by your imagination and what we know of as current reality. As as we know, over time in physics, our perception of things seem to change as we discover more things. So these are my references. I appreciate your time. Thank you.